What if I told you that right now, something travelling at 55 kilometers per second is crossing our solar system fast enough to span from New York to Los Angeles in under 2 minutes? 3I-ATLAS arrived in July 2025, our third confirmed visitor from interstellar space, following a trajectory that brings it safely past Earth at 300 million kilometers. But here's what should keep you awake at night. Speed changes everything in cosmic collisions. Energy scales with velocity squared, making this wandering nucleus, no larger than a mountain, potentially more devastating than objects 10 times its size. What if those orbital calculations were different by just a few kilometers? What if this ancient traveler, formed around a distant star billions of years ago, had Earth in its crosshairs instead? Tonight, we explore scenarios where visitors from other star systems become agents of planetary transformation, examining how a small rock moving faster than any human-made object could trigger cascading effects lasting decades. Stay with us to discover not just what would happen if 3I-ATLAS struck Earth, but how humanity might be able to write a different ending to this story. The telescope images arrive in neat digital packages, each frame time-stamped and calibrated. Against the fixed backdrop of distant stars, something moves. The motion is subtle at first, requiring careful comparison between exposures taken hours or days apart. But the pattern is unmistakable. This object follows a trajectory that originates far beyond the realm of planets and asteroids. It's a visitor from interstellar space. In July 2025, the ATLAS Survey Network confirmed the discovery of 3I-ATLAS, catalogued formally as C 2025-N1. Follow-up observations by Hubble and ground-based telescopes began constraining its physical properties. The nucleus appeared to measure somewhere between a few hundred meters and perhaps 5 or 6 kilometers across, though the smaller estimates seemed more consistent with its brightness and activity levels. Most importantly, orbital calculations revealed a hyperbolic trajectory that would bring it no closer than 1/8 astronomical units from Earth. That's a comfortable margin of safety, about 270 million kilometers. But what catches the attention of planetary defense specialists is not where this object is going, but where objects like it could go. The discovery of 3I-ATLAS marks only the third confirmed interstellar object detected passing through our solar system. The first, Oumuamua, appeared in 2017 as a tumbling, elongated body that displayed mysterious non-gravitational acceleration as it rounded the Sunday. The second, 2I, Borisov, behaved like a more typical comet, developing dust and gas tails as solar heating drove off surface materials. Each detection adds to our growing understanding of how common these wandering objects might be. Current estimates suggest that interstellar visitors arrive in the inner solar system perhaps once per year, though most go undetected due to their small size and rapid motion. The Rubin Observatory, now entering full science operations, should dramatically improve our detection rate. Some projections suggest it might find dozens of interstellar objects annually, once its deep, wide surveys reach full cadence. The physics of these encounters follows predictable rules. Interstellar objects arrive with velocities typically ranging from 45 to 65 kilometers per second relative to our Sunday. That's roughly twice the speed of long-period comets emerging from the Oort cloud, and nearly 3 times faster than typical near-Earth asteroids. The extra velocity translates directly into kinetic energy. When objects collide, energy scales with the square of velocity, making speed the dominant factor in determining impact effects. Consider a simple comparison. A 1-kilometer stony asteroid moving at 20 kilometers per second carries about 65,000 megatons of kinetic energy. Scale that same object up to comet composition and interstellar velocity, and the energy jumps to roughly 114,000 megatons. The difference lies entirely in that velocity-squared relationship. Even a smaller interstellar object can rival the destructive potential of a much larger asteroid. The historical precedent that shapes current thinking about major impacts occurred 66 million years ago at Chicxulub. That collision involved an object perhaps 10 to 12 kilometers across, moving at an estimated 20 to 30 kilometers per second. The result was a crater 150 to 180 kilometers wide and a mass extinction that eliminated roughly 75% of Earth's species. The energy release approached 100 million megatons, enough to inject vast quantities of dust and debris into the stratosphere. Modern research has refined our understanding of what made that ancient impact so devastating. A 2023 study published in Nature Geoscience analyzed sediment cores from the impact boundary and found evidence for prolonged atmospheric dust loading. Fine silicate particles measuring between 0, 8, and 8 micrometers appear to have remained suspended in the atmosphere for 15 to 20 years. Photosynthesis may have been severely disrupted for the first 2 years, with lesser effects persisting for over a decade. The Chicxulub impact occurred when an object roughly the size of Mount Everest collided with a shallow carbonate platform in what is now the Gulf of Mexico. The target geology was particularly unfortunate, rich in sulfate minerals that vaporized upon impact and formed long-lived stratospheric aerosols. But even without that geological bad luck, the sheer quantity of fine dust ejected by such a large, fast-moving impactor would have had severe climate consequences. This raises uncomfortable questions about smaller impacts. How big does an object need to be to trigger significant atmospheric effects? The answer depends on velocity, composition, impact angle, and target geology. But the general principle is clear. Fast-moving comets punch above their weight class. A 3-kilometer interstellar comet arriving at 55 kilometers per second would deliver roughly 3 million megatons of energy, enough to excavate a crater 60 to 90 kilometers across and inject enormous quantities of dust into the stratosphere. The probability of such an impact in any given year remains vanishingly small. Current estimates suggest that kilometer-scale interstellar objects might strike Earth perhaps once every 10 to 100 million years. But probability and possibility are different concepts. The question we explore is not whether such an impact will occur, but what would happen if it did. The answer shapes how we think about detection systems, deflection technologies, and the broader challenge of planetary defense. For now, 3I-ATLAS continues its peaceful journey through the inner solar system. It will reach perihelion at about 1.4 astronomical units from the Sun on the 30th of October, 2025, then begin the long journey back to interstellar space. Telescopes around the world will track its progress, measuring its composition and behavior as solar heating activates its surface. We'll learn something new about the materials that formed around other stars billions of years ago, but we also carry forward a different thread of inquiry. In the careful mathematics of orbital mechanics and impact physics, in the patient work of sky surveys and threat assessment, we find the tools needed to recognize when a visitor from the stars might be something more than scientifically interesting. The universe contains multitudes of wandering objects, and not all of them will pass by peacefully. We prepare for the ones that don't. Part 2. The last time a big one hit. The evidence lies buried in a thin layer of clay found around the world. In some places, it's just a few centimeters thick. In others, it forms a distinct band of darker sediment between limestone layers. But everywhere it appears, this boundary marks the same moment in Earth's history, the end of the Cretaceous period, 66 million years ago, when an object from space reshaped the planet and ended the age of dinosaurs. The Chicxulub crater stretches across 150 to 180 kilometers of what is now Mexico's Yucatan Peninsula. Much of it lies buried under younger sediments, but gravity surveys and drilling campaigns have mapped its structure in detail. The crater's size suggests an impactor roughly 10 to 12 kilometers across, moving at perhaps 20 to 30 kilometers per second when it struck the shallow carbonate platform that covered this region during the late Cretaceous. The energy release approached 100 million megatons of TNT equivalent. To put that in perspective, it's roughly 6,600 times more powerful than the largest nuclear weapon ever tested. But the raw energy tells only part of the story. What made this impact so devastating was where that energy went and how long its effects persisted in Earth's atmospheric and climate systems. When the impactor struck, it vaporized both itself and enormous volumes of target rock. The collision excavated the crater in a matter of minutes, hurling molten debris on ballistic trajectories that reached around the globe. Some of this material fell back to Earth within hours, heating the atmosphere and igniting wildfires across entire continents. Larger chunks took days or weeks to return, creating a secondary bombardment that extended the period of atmospheric heating. But the most significant long-term effect came from finer materials that remained suspended in the stratosphere for years or decades. Recent research has transformed our understanding of this atmospheric loading and its consequences for life on Earth. A 2023 study, led by researchers at the University of Texas, analyzed sediment cores from North Dakota that preserve an exceptionally detailed record of the impact boundary. The analysis revealed abundant fine silicate dust particles measuring between 0.8 and 8 micrometers in diameter. These particles appear to have remained suspended in the atmosphere for 15 to 20 years after the impact, with the highest concentrations persisting for the first 5 to 8 years. During the initial 2-year period, dust loading was so severe that photosynthesis appears to have been almost completely shut down on a global scale. This finding represents a significant shift in scientific thinking about the Chicxulub extinction. Earlier models focused primarily on sulfur aerosols created when the impact vaporized sulfate-rich target rocks, or on soot from impact-triggered wildfires. Both of these materials would have cooled the climate and reduced sunlight reaching Earth's surface. But fine silicate dust appears to have been equally important, and it lingered in the atmosphere much longer than previously recognized. The implications extend far beyond academic paleontology. If fine dust can remain suspended for decades after a major impact, then the threshold for triggering significant climate effects may be lower than previously thought. A smaller impactor could still inject enough dust into the stratosphere to disrupt photosynthesis for multiple growing seasons, potentially causing widespread ecosystem collapse even without the sulfur-rich target geology that amplified the Chicxulub effects. The geological evidence also reveals other impact consequences that cascaded through Earth's interconnected systems. Massive tsunamis swept across shallow seas, leaving chaotic deposits of jumbled rocks and fossils. Acid rain, generated by sulfur and nitrogen compounds created in the impact fireball, altered ocean chemistry for thousands of years. The combination of immediate thermal effects, prolonged darkness, and chemical perturbations created what researchers now call the impact winter that followed the Chicxulub collision. This ancient catastrophe provides our best natural laboratory for understanding how impacts affect planetary systems. The boundary layer preserves evidence not just of the immediate destruction, but of the longer-term recovery. Life did eventually rebound, but it took millions of years for biodiversity to return to pre-impact levels. The mammals that survived went on to diversify and eventually give rise to human civilization, but the path from impact to recovery was neither quick nor simple. The lessons from Chicxulub shape modern thinking about asteroid and comet threats. We now understand that atmospheric effects can extend far beyond the immediate impact region, and that relatively modest amounts of fine dust can have disproportionate climate consequences if they reach the stratosphere and remain suspended for years rather than months. This understanding also informs current efforts to model the potential effects of smaller impacts. Computer simulations suggest that objects as small as 500 meters to 1 kilometer across could trigger regional climate effects if they strike at high velocity and inject sufficient dust into the upper atmosphere. The exact threshold depends on many factors, including impact velocity, target geology, and the size distribution of ejected particles. The Chicxulub precedent also demonstrates the importance of impact angle and target selection. The Mexico impact occurred at an angle close to 60 degrees from vertical, which was nearly optimal for maximizing both the amount of vaporized rock and the efficiency of debris injection into the stratosphere. A more grazing impact might have created a larger crater but lofted less material skyward. A steeper impact might have dug deeper but created a more localized debris pattern. Perhaps most importantly, the Chicxulub boundary reminds us that major impacts are not abstract possibilities but documented parts of Earth's history. The crater exists, the boundary layer exists. The extinction is recorded in fossils found around the world. What happened 66 million years ago could happen again, though the timescales involved suggest we're more likely to face smaller but still significant impacts in the foreseeable future. As we consider scenarios involving objects like 3I-ATLAS, we carry forward these lessons from deep time. The physics of high-velocity collisions follows predictable rules. The climate system responds to atmospheric dust loading in ways we can model and anticipate. The biosphere shows remarkable resilience over geological timescales, but that resilience has limits and operates on timescales far longer than human civilization. The boundary between the Cretaceous and Paleogene periods marks more than just an extinction event. It represents a transition between one kind of world and another, orchestrated by a visitor from space that arrived at precisely the wrong moment. We study that transition not to dwell on ancient catastrophes, but to better understand the forces that could shape our own future. Part 3. Anatomy of a space rock. The mathematics of destruction begins with a simple equation: kinetic energy equals 1/2 mass times velocity squared. This relationship, fundamental to all high-speed collisions, explains why comets arriving from interstellar space pose such significant threats despite their relatively modest size. Velocity dominates the energy calculation, and interstellar visitors arrive fast. Consider the basic physics that governs these encounters. A typical stony asteroid from the main belt has a density of roughly 6 grams per cubic centimeter, comparable to granite or concrete. These objects follow elliptical orbits that bring them into the inner solar system at speeds averaging 17 to 23 kilometers per second when they cross Earth's path. Their velocity represents a balance between the gravitational acceleration they've gained falling toward the Sun and the orbital motion they inherited from their formation in the asteroid belt. Comets follow a different pattern. Most long-period comets originate in the Oort cloud, a spherical shell of icy debris that extends perhaps 50,000 astronomical units from the sunday. When gravitational perturbations nudge these objects sunward, they fall along nearly parabolic trajectories, accelerating as they approach the inner solar system. By the time they cross Earth's orbit, they're typically moving at 45 to 65 kilometers per second. But interstellar objects like Oumuamua and 3I-ATLAS arrive with even higher velocities. They've spent millions or billions of years traveling through space, unbound to any star. When they encounter our solar system, they follow hyperbolic trajectories that carry them past the Sun and back to interstellar space. Their velocities at Earth's distance from the Sun typically range from 45 to 72 kilometers per second, depending on their approach angle and the Sun's gravitational focusing effect. The density difference between asteroids and comets also affects impact calculations. Comet nuclei are loose collections of ice, rock, and organic compounds with densities typically ranging from 0.4 to 0.8 grams per cubic centimeter. They're roughly as dense as fresh snow or pumice stone. This lower density partially compensates for their higher velocity, but the velocity squared term in the energy equation ensures that comets still pack a much larger punch than asteroids of similar size. Let's work through some concrete examples. A 1 kilometer stony asteroid striking Earth at 20 kilometers per second would deliver roughly 65,000 megatons of kinetic energy. Scale that object up to comet density and interstellar velocity, and the energy jumps to approximately 114,000 megatons. The 75% increase comes entirely from the higher impact speed. Now, consider a smaller interstellar object. A 500-meter comet nucleus arriving at 55 kilometers per second would release about 14,000 megatons of energy. That's comparable to a 700-meter stony asteroid at typical near-Earth approach speeds. Even Oumuamua, with its estimated dimensions of roughly 100 by 30 by 30 meters, would deliver about 190 megatons if it struck Earth directly. That's nearly 20 times more energy than the 1,908 Tunguska event, which flattened 2,000 square kilometers of Siberian forest. The energy scaling continues upward in dramatic fashion. A 3-kilometer interstellar comet would release roughly 1 million megatons upon impact. That approaches the energy range estimated for the Chicxulub impact that ended the dinosaurs. A hypothetical 6-kilometer interstellar object would deliver nearly 20 million megatons, well into the realm of mass extinction events. These energy calculations provide the foundation for understanding impact effects, but translating energy into real-world consequences requires considering additional factors. The angle of impact plays a crucial role in determining how that energy gets distributed. Most impacts occur at angles between 30 and 60 degrees from vertical, with 45 degrees being the most probable angle based on geometric considerations. Shallow impacts create different damage patterns than steep ones. A grazing collision at 15 to 30 degrees tends to produce an elongated crater and distribute debris in a distinctive butterfly pattern downrange from the impact site. The impactor may also skip or fragment during its passage through the atmosphere, creating multiple impact points along its trajectory. Conversely, a steep impact concentrates more energy in a smaller area and tends to excavate a deeper, more circular crater. The size of the resulting crater depends on the impactor's energy and the properties of the target material. As a rough rule of thumb, impact craters end up 10 to 20 times larger than the impactor itself, though this ratio varies significantly with impact velocity and target geology. A 1-kilometer object typically creates a crater 15 to 20 kilometers across. A 3-kilometer impactor might excavate a crater 60 to 90 kilometers in diameter, but not all impacts create craters. Smaller objects, typically those under a few hundred meters in diameter, often break apart in the atmosphere before reaching the ground. The resulting airburst can still cause significant damage over a wide area through blast waves and thermal radiation, but without the deep excavation and massive debris production of a surface impact. The transition between airbursts and crater formation depends on the object's size, velocity, density, and internal strength. Loosely bound comet nuclei tend to fragment more readily than solid metallic asteroids. A 100-meter iron asteroid might survive atmospheric entry intact, while a 500-meter comet nucleus might break apart at high altitude. This variability makes it difficult to predict impact effects precisely without detailed knowledge of the object's composition and structure. The atmospheric passage itself adds another layer of complexity. Objects entering at interstellar velocities experience tremendous dynamic pressure as they plow through increasingly dense air. The leading surface heats to thousands of degrees, creating a glowing plasma sheath that can be visible from hundreds of kilometers away. The pressure differential between the leading edge and the trailing surface can tear weak objects apart, sometimes explosively. These physical processes shape the final impact effects in ways that pure energy calculations cannot capture. A single large impactor creates different hazards than the same mass distributed among multiple smaller fragments. Surface impacts generate different secondary effects than high-altitude airbursts. Ocean impacts create tsunamis but less atmospheric dust, while continental impacts favor dust production over water displacement. Understanding these nuances becomes crucial when modeling the potential effects of specific objects like 3I-ATLAS. The energy released by a hypothetical impact provides the starting point for the analysis, but the details of crater formation, atmospheric injection, and secondary effects determine whether the result is a regional disaster or a global catastrophe. The physics remains consistent across all scales. Mass, velocity, and basic conservation laws govern every collision between objects in space. But the expression of those physical principles through Earth's complex systems creates a rich variety of possible outcomes. We map these possibilities not to dwell on destruction, but to better understand the forces at work when worlds collide. Part 4. If 3I-ATLAS came close, imagine 3I-ATLAS following a different trajectory, one that would bring it not 270 million kilometers from Earth, but close enough to see with the naked eye. The mathematics of comet brightness depend on both its distance from the Sun and its distance from Earth, modified by the level of activity as solar heating drives off dust and gas from the nucleus surface. The basic relationship follows a well-established formula. Apparent magnitude equals the absolute magnitude plus 5 times the logarithm of the Earth distance plus 2. 5 times an activity index times the logarithm of the solar distance. For most comets, the activity index ranges from 2 to 5, with higher values indicating more vigorous outgassing as the nucleus approaches the sunday. But this standard calculation misses one of the most dramatic effects in comet observing: forward scattering. When Earth lies nearly along the line between the Sun and the comet, sunlight scattered by dust particles in the coma and tail can create spectacular brightness enhancements. The effect is similar to looking toward the Sun through a cloud of fine particles. Individual grains that would be invisible under normal circumstances suddenly blaze with reflected light. The most famous recent example occurred in 2007 with Comet McNaught, designated C 2006P1. As it rounded the Sun, forward scattering boosted its apparent magnitude to between -5 and -5, making it visible in broad daylight for observers in the southern hemisphere. The comet's dust tail stretched across 35 degrees of sky, creating one of the most spectacular celestial displays of the modern era. McNaught's performance demonstrates what becomes possible when a reasonably large comet nucleus approaches the Sun at just the right geometry. The comet's nucleus was estimated at roughly 25 kilometers across, much larger than the likely size of 3I-ATLAS. But even a smaller nucleus can put on an impressive show under favorable circumstances. Consider Comet Hale-Bopp, which reached magnitude -1.8 during its 1997 apparition and remained visible to the naked eye for over 18 months. Hale-Bopp's exceptional longevity came from its massive nucleus, estimated at 40 to 60 kilometers in diameter. That size translated into enormous reserves of ice and dust that continued outgassing long after the comet passed perihelion. But Hale-Bopp never came particularly close to Earth, maintaining a distance of roughly 1.3 astronomical units at its nearest approach. Now imagine 3I-ATLAS on a hypothetical trajectory that brings it much closer to Earth, perhaps 0.1 astronomical units, or roughly 15 million kilometers. That's about 40 times closer than the Moon, well within the orbits of some artificial satellites. At this distance, even a modest nucleus a few kilometers across could become spectacular. The forward scattering effect would likely dominate the brightness calculation. If the geometry aligned properly, placing Earth nearly between the Sun and the approaching comet, 3I-ATLAS could easily reach negative magnitudes and become visible in daylight. The exact brightness would depend on the nucleus size, activity level, and dust production rate, all of which remain uncertain for this particular object. The comet's appearance would evolve rapidly as it approached. Weeks or months before closest approach, it might appear as a modest telescopic object, perhaps magnitude 8 to 10, visible only to experienced observers with good equipment. As it drew closer and solar heating increased, the coma would expand and brighten. A tail would begin to form, at first just a faint extension visible in long exposure photographs. But, as 3I-ATLAS approached its closest point to Earth, the tail structure would become increasingly dramatic. Comets typically develop two distinct tails with different characteristics. The dust tail appears yellowish-white and curves gently away from the Sun as solar radiation pressure pushes particles along curved trajectories. The ion tail glows blue-green from excited gas molecules and points nearly straight away from the Sun, shaped by the solar wind's magnetic field. During close approach, both tails would be visible to the naked eye. The dust tail might span 10 to 20 degrees of sky, creating a broad fan-shaped structure that would dominate the twilight sky. The ion tail could extend even further, appearing as a narrow streak of blue-green light stretching across the heavens. Night-to-night changes would be easily visible as the comet's motion and evolving solar wind conditions altered the tail structure. Some comets also develop sodium tails, which appear yellow and can extend for millions of kilometers. These form when solar radiation breaks down dust particles and liberates sodium atoms, which then glow brightly at specific wavelengths. The sodium tail often appears separate from both the dust and ion tails, adding a third component to the comet's spectacular appearance. Photography would capture details invisible to the eye. Long exposures might reveal complex structure within the coma, including jets and fans created as specific areas of the nucleus become active. The tail would show intricate knots and streamers as magnetic field lines in the solar wind interact with the ion tail. Some observers might detect the antitail, a narrow spike that appears to point toward the Sun and results from dust particles distributed along the comet's orbital path. But perhaps the most memorable aspect would be the comet's motion against the stellar background. Most astronomical objects appear essentially fixed in position from night to night. A bright comet moves visibly, tracing a path through constellations and creating a dynamic display that changes from hour to hour. During closest approach, 3I-ATLAS might move several degrees per day, fast enough that its position would shift noticeably over the course of a single observing session. The hypothetical close encounter would also provide unprecedented opportunities for scientific study. Space-based telescopes could resolve details of the nucleus structure and composition. Ground-based spectrographs could analyze the chemical composition of gas and dust streaming from the comet. Radar observations might map the nucleus shape and rotation state. The combination would offer insights into the materials and processes that shaped planetary systems around other stars billions of years ago. Of course, any trajectory that brought 3I-ATLAS close enough for such observations would also raise questions about impact probability. The same orbital mechanics that could create a spectacular sky show could, with slightly different initial conditions, place the comet on a collision course with Earth. We explore these more concerning possibilities in the scenarios that follow. For now, we're left with the safer spectacle of a comet that passes close enough to inspire wonder, but far enough away to avoid danger. The real 3I-ATLAS will provide no such show, maintaining its safe distance as it completes its brief visit to our solar system. But the possibility remains that future interstellar visitors might follow more dramatic trajectories, creating displays that would rival the greatest comets in human history. Part 5. How we'd find and track a threat like this. The discovery of 3I-ATLAS began with an automated detection algorithm scanning through thousands of images collected by the ATLAS survey network. Each frame captured a small patch of sky, typically covering about 30 square degrees, with enough sensitivity to detect objects as faint as magnitude 19 or 20. The computer software compared new images with reference frames taken weeks or months earlier, flagging anything that had moved or changed brightness. Most detections turn out to be main belt asteroids, their steady motion betraying their membership in the vast population of rocky debris orbiting between Mars and Jupiter. Others are near-Earth asteroids following more eccentric paths that occasionally bring them close to our planet. But a few detections each year reveal something different, objects moving so quickly across the sky that they can only be visitors from far beyond the realm of planets. The global network that enables these discoveries has grown dramatically over the past decade. ATLAS operates telescopes in Hawaii, South Africa, and Chile, scanning the entire visible sky every few nights. Pan-STARRS surveys from Hawaii with deeper sensitivity but slower cadence. The Catalina Sky Survey operates from Arizona, focusing on the search for near-Earth asteroids but occasionally finding more exotic visitors. The Zwicky Transient Facility in California combines high speed with good sensitivity, making it particularly effective at catching fast-moving objects. When any of these surveys detects a potentially interesting object, observations flow rapidly to the Minor Planet Center in Massachusetts, which serves as the global clearinghouse for asteroid and comet discoveries. Automated systems there compute preliminary orbits and determine whether follow-up observations are urgently needed. For objects on potentially hazardous trajectories, alerts go out within hours to observatories around the world. NASA's Planetary Defense Coordination Office coordinates the American response to asteroid and comet threats. Established in 2016, the PDCO works with international partners through the International Asteroid Warning Network and the Space Mission Planning Advisory Group to ensure that threatening objects are tracked accurately and that impact warnings reach the PDCO, appropriate authorities in time for effective response. But the current system has significant limitations. Most ground-based surveys can only observe during clear, dark nights, losing roughly half of all potential observing time to weather and daylight. Objects approaching from the direction of the Sun remain essentially invisible until they've already passed their closest point to Earth. And the surveys are biased toward detecting larger, brighter objects, potentially missing smaller but still dangerous impactors until they're very close. The next few years will bring major improvements to this detection network. The Rubin Observatory in Chile is now entering full science operations with its 8 4-meter telescope and 3 2-gigapixel camera. This facility will survey the entire southern sky every few nights to unprecedented depth, with sophisticated software designed to identify moving objects and link observations separated by days or weeks. Early simulations suggest that Rubin might detect anywhere from a few to several dozen interstellar objects per year, depending on their size, distribution, and activity levels. The observatory's rapid cadence and deep sensitivity make it particularly well suited for finding fast-moving objects that might be missed by surveys with longer revisit times. Equally important is the development of new linking algorithms that can connect observations of the same object even when separated by long time intervals. Traditional techniques require detecting an object on at least 3 nights within a relatively short time window. But advanced algorithms like HelioLIN-C3D can link observations separated by months or even years, effectively mining archival databases for objects that were observed but not recognized. These computational advances have already paid dividends. The Thor algorithm has identified tens of thousands of previously unknown asteroids by reanalyzing archival survey data with modern linking techniques. As Rubin begins generating terabytes of astronomical data each night, similar approaches will undoubtedly reveal many more objects hiding in the vast stream of observations. The space-based component of planetary defense is also advancing. NEO-Surveyor, a specialized infrared telescope designed to find and characterize near-Earth asteroids, is scheduled for launch no earlier than late 2027, with NASA committed to launch no later than June 2028. Operating from a gravitationally stable orbit near the L1 Lagrange point, NEO-Surveyor will be able to observe continuously without interference from weather or daylight. Infrared observations offer unique advantages for asteroid detection. Many asteroids that appear faint in visible light shine brightly in thermal emission, making them easier to detect and characterize. NEO-Surveyor will be particularly effective at finding dark asteroids that approach Earth from the direction of the Sun, filling a major gap in current ground-based surveys. The combination of Rubin's optical surveys and NEO-Surveyor's infrared observations should dramatically improve our ability to detect potentially threatening objects years or decades before impact. But detection is only the first step in planetary defense. Once an object is found, precise orbit determination becomes crucial for assessing impact probability and planning potential deflection missions. Modern orbit determination relies on a statistical approach called least squares fitting, which finds the trajectory that best matches all available observations while accounting for measurement uncertainties. For newly discovered objects, the initial orbit is often quite uncertain, represented by an error ellipse that can span millions of kilometers at the object's predicted future position. As more observations accumulate, the uncertainty ellipse shrinks rapidly. This improvement follows predictable mathematical relationships that allow astronomers to estimate how many observations will be needed to achieve a given level of precision. For most objects, a few weeks of tracking reduces the position uncertainty to manageable levels. But some cases require special attention. Objects on nearly parabolic or hyperbolic orbits, like long-period comets and interstellar visitors, present particular challenges for orbit determination. Their high velocities and short observing windows mean that small errors in early observations can translate into large uncertainties in their future positions. The statistical framework for managing these uncertainties has been developed through years of experience with potentially hazardous asteroids. When an object is first discovered on a trajectory that might intersect Earth, it typically receives a rating of 1 on the Torino scale, indicating that it deserves routine monitoring but poses no immediate cause for concern. As observations accumulate and the orbit becomes better determined, the Torino rating usually drops to 0 as the impact probability becomes negligibly small. Occasionally, however, an object maintains a significant impact probability even after extensive observation. These cases receive higher Torino ratings and trigger more intensive monitoring efforts. The European Space Agency maintains a continuously updated risk list of objects with non-zero impact probabilities, tracking how these probabilities evolve as new observations become available. The most famous example of this process involved asteroid 9994 2 Apophis, which briefly reached Torino scale 4-inch 2004 when initial observations suggested a small but significant probability of Earth impact in 2029. Subsequent observations, including radar measurements that precisely determined the asteroid's position and spin state, ruled out the 2029 impact and reduced the probability of later impacts to essentially zero. International coordination becomes crucial when dealing with objects that might pose genuine threats. The International Asteroid Warning Network provides a framework for sharing observations and coordinating follow-up campaigns. The Space Mission Planning Advisory Group works on the more challenging problem of coordinating international responses to confirmed threats, including decisions about deflection missions and impact mitigation strategies. Recent planetary defense exercises have highlighted both the strengths and weaknesses of current international coordination mechanisms. The Biennial Planetary Defense Conference includes detailed tabletop exercises where participants work through hypothetical impact scenarios, making decisions about observation campaigns, deflection missions, and civil defense preparations under realistic time pressure and uncertainty. These exercises consistently demonstrate that early detection provides the greatest number of response options. An asteroid or comet discovered decades before impact can be deflected with relatively modest velocity changes applied at the right time and place. Objects discovered only months or years before impact require much more aggressive intervention, with higher mission costs, greater technical risks, and less certain outcomes. The expanding network of survey telescopes and improved orbit determination techniques are pushing detection times steadily earlier. Current surveys routinely find near-Earth asteroids years or decades before their close approaches to Earth. Future facilities like Rubin and NEO-Surveyor should extend this early warning capability to smaller and more difficult objects, including the interstellar visitors that arrive without advance notice. But challenges remain. Objects approaching from the direction of the Sun will always be difficult to detect until after they pass perihelion. Very dark objects may remain invisible to optical surveys until they're uncomfortably close. And the sheer volume of data generated by next-generation surveys will require continued advances in automated analysis techniques to avoid missing important discoveries in the flood of routine detections. The story of 3I-ATLAS illustrates both the capabilities and limitations of current detection networks. The object was discovered promptly after it became bright enough for ground-based surveys to detect. Follow-up observations quickly established its interstellar origin and safe trajectory. But if this same object had been approaching on a collision course with Earth, we would have had only a few months of warning time to mount any kind of response. That timeline underscores the importance of continued investment in survey capabilities and international coordination mechanisms. The universe contains countless objects following trajectories we cannot predict. Our ability to detect them early and respond effectively will determine whether future encounters with visitors from the stars remain scientifically interesting or become existentially challenging. Part 6. How big is bad? The challenge of communicating asteroid and comet risk to the public led to the development of two complementary scales that translate complex orbital mechanics into simple numerical ratings. The Torino scale, named after a 1999 conference in Italy, provides a straightforward 0 to 10 rating that combines impact probability with estimated consequences. The Palermo scale offers a more sophisticated logarithmic measure that compares specific threats to the background risk from all possible impacts. Most newly discovered objects begin their lives at Torino Scale 1, indicating that current observations suggest a collision is possible but extremely unlikely. This rating triggers routine monitoring but no special concern. As additional observations refine the orbit, the vast majority of objects drop to Torino 0, meaning that collision has been ruled out or reduced to essentially zero probability. Only a handful of objects have ever reached higher Torino ratings, and none have maintained ratings above 4 for extended periods. The European Space Agency maintains a continuously updated risk list that tracks all objects with non-zero impact probabilities. This list typically contains several dozen entries, ranging from small asteroids with minute collision chances to larger objects with somewhat higher probabilities. The list changes daily as new observations either eliminate objects entirely or shift their impact probabilities up or down. Understanding these risk scales requires grappling with the statistical nature of impact prediction. When astronomers calculate that an asteroid has a 1 in 10,000 chance of hitting Earth in 2087, they're not making a definitive prediction about what will happen in that specific year. Instead, they're quantifying their uncertainty about the object's precise trajectory based on current observational data. This uncertainty shrinks predictably as more observations accumulate. An asteroid discovered today might have a position uncertainty of several thousand kilometers when projected forward 50 years, but each additional night of observations narrows that uncertainty ellipse, typically by factors of 2 to 10, depending on the observation quality and time baseline. The background impact rate provides crucial context for evaluating specific threats. Statistical analyses of craters and atmospheric entry events suggest that kilometer-scale objects strike Earth roughly once every 500,000 to 1 million years. Smaller but still significant objects in the 100 to 500 meter range arrive perhaps once every 10,000 to 100,000 years. These numbers represent averages over geological time. The actual intervals between impacts vary widely due to the random nature of orbital evolution. Catalogue completeness becomes a critical factor in risk assessment. NASA's current surveys have discovered more than 90% of near-Earth asteroids larger than 1 kilometer, meaning that we've probably found most objects capable of causing global catastrophes. But completeness drops rapidly for smaller sizes. Perhaps 25% of 300-meter asteroids remain undiscovered, and the fraction of unknown objects rises sharply for smaller sizes. Long-period comets and interstellar objects present special challenges for risk assessment. These visitors arrive from far beyond the realm of planets, following trajectories that cannot be predicted in advance. Current statistical models suggest that long-period comets might strike Earth once every few million years, while interstellar impacts might occur once every 10 to 100 million years. But these estimates carry enormous uncertainties due to the small number of observed objects. The velocity difference between asteroids and comets significantly affects impact consequences. Long-period comets typically arrive at 50 to 60 kilometers per second, compared to 17 to 25 kilometers per second for most near-Earth asteroids. Since kinetic energy scales with velocity squared, a comet delivers roughly 6 times more energy than an asteroid of equal mass. Combined with their typically lower density, comets end up carrying about 30% more kinetic energy per unit diameter than rocky asteroids. This velocity advantage makes comets particularly concerning despite their relative rarity. A 500-meter comet nucleus arriving at 55 kilometers per second delivers roughly the same energy as a 600-meter stony asteroid at 20 kilometers per second. The comet's higher speed more than compensates for its lower density, creating significant destructive potential in a relatively small package. Interstellar objects like Oumuamua and 3I-ATLAS add another layer of uncertainty to risk calculations. Their approach velocities can reach 70 km per second or higher, depending on their trajectory relative to the solar system's motion through space. At these speeds, even relatively small objects carry enormous kinetic energy. A 100-meter interstellar object might deliver 200 to 400 megatons upon impact, comparable to a 200-meter asteroid from the main belt. The challenge facing planetary defense specialists is that impact consequences scale non-linearly with object size and velocity. A doubling of diameter increases the destructive energy by a factor of 8, assuming constant density. A doubling of velocity increases energy by a factor of 4. These scaling relationships mean that the boundary between regional and global catastrophes is surprisingly narrow. Current research suggests that objects in the 300 to 500 meter range represent a threshold where local and regional effects begin to merge into broader consequences. Impacts in this size range can trigger multi-year climate effects if they inject sufficient dust into the stratosphere, particularly if they strike sulfate-rich target rocks that amplify the atmospheric loading. The 1 kilometer threshold has traditionally been considered the boundary between regional and global catastrophes, but recent climate modeling suggests that this boundary might be lower for high-velocity impacts or unfortunate target geology. A 750-meter comet striking a carbonate platform might cause more severe climate effects than a 1-2-kilometer asteroid hitting crystalline rock due to differences in impact velocity and the chemical composition of ejected materials. These scaling relationships inform current planetary defense priorities. Objects large enough to cause global catastrophes are rare and mostly catalogued. Objects too small to cause significant damage are numerous, but not worth the cost of comprehensive surveys. The focus falls on intermediate sizes that combine significant destructive potential with realistic detection and deflection possibilities. Future survey programs like Rubin Observatory and NEO Surveyor will push detection capabilities towards smaller and more diverse populations of potentially hazardous objects. These facilities should find thousands of new near-Earth asteroids in the 50 to 500 meter range, providing a much more complete picture of the intermediate scale impact risk. But statistical projections based on current knowledge suggest that any individual person's lifetime risk from asteroid or comet impacts remains extremely small, roughly comparable to the risk of being struck by lightning. The challenge for planetary defense is not managing high probability events, but preparing for low probability events with potentially catastrophic consequences. The mathematics of risk assessment provides tools for thinking systematically about these low probability, high consequence scenarios. But mathematics alone cannot capture the full complexity of how human societies might respond to impact threats, or how international cooperation might evolve under the pressure of potential catastrophe. We carry these questions forward as we explore the specific scenarios that could unfold if objects like 3I-ATLAS arrived on collision trajectories. Part 7. 3I-ATLAS Impact. Part 1. Mechanics and Immediate Devastation. The physics of collision begins the moment our hypothetical 3I-ATLAS encounters Earth's atmosphere at 55 km per second. At this velocity, the comet nucleus compresses the air ahead of it to pressures exceeding 100 atmospheres, heating the gas to temperatures comparable to the Sun's surface. The leading edge of the object begins to vaporize almost immediately, creating a brilliant plasma sheath that would be visible from space. For our analysis, we consider two scenarios that bracket the range of possibilities suggested by early observations of the real 3I-ATLAS. Case A assumes a nucleus diameter of 500 meters delivering roughly 14,000 megatons of kinetic energy. Case B scales up to a 3-kilometer nucleus carrying over 3 million megatons. Both scenarios assume typical comet composition with a density of 0. 6 grams per cubic centimeter and an impact angle of 45 degrees from vertical. The 500-meter case represents what planetary defense specialists call a regional catastrophe. The object would likely fragment during atmospheric passage, with some pieces reaching the ground while others explode at various altitudes. The combined effects of airbursts and surface impacts would devastate an area roughly the size of a small country, with significant but survivable consequences for the broader region. Dynamic pressure during atmospheric entry determines whether an object survives to create a crater or breaks apart in an airburst. The pressure scales with atmospheric density and the square of velocity, reaching maximum values at altitudes between 20 and 40 kilometers depending on the entry angle. Loosely bound comet nuclei typically begin fragmenting when dynamic pressure exceeds a few 100,000 pascals, equivalent to about 3 atmospheres. A 500-meter comet nucleus would likely fragment into dozens of pieces during its final few seconds of flight. The largest fragments might reach the ground moving at several kilometers per second, excavating craters a few hundred meters to a few kilometers across. Smaller pieces would explode at various altitudes, creating a sequence of airbursts that would pummel the impact region with overlapping shock waves. The combined crater from all fragments would probably measure 10 to 12 kilometers in diameter, surrounded by a zone of severe destruction extending 50 to 100 kilometers from the impact point. The initial fireball would vaporize everything within the first few kilometers, creating temperatures exceeding 5,000 degrees Celsius. Thermal radiation from the fireball would ignite fires across hundreds of square kilometers, while the blast wave would level most structures within 30 to 50 kilometers. Case B, the 3-kilometer scenario, represents a fundamentally different class of event. An object this large would probably survive atmospheric passage largely intact, striking the ground with most of its cosmic velocity preserved. The resulting crater would measure 60 to 90 kilometers across, comparable to well-known impact structures like the Barringer crater in Arizona, but scaled up by a factor of 1,000 in area. The excavation process would unfold over approximately 2 minutes, beginning with the formation of a transient cavity, perhaps 150 kilometers across and 30 kilometers deep. Shock waves would fracture bedrock across an even wider area, while the expanding fireball would vaporize millions of tons of target rock and comet material. Much of this vaporized material would be injected into the atmosphere on ballistic trajectories, eventually falling back to Earth as a global layer of impact debris. The choice between continental and oceanic impact sites dramatically affects the immediate consequences. A continental impact maximizes dust injection into the atmosphere, but limits the geographic range of immediate destruction. An oceanic impact spreads the immediate effects over a much wider area through tsunami generation, but may inject less dust into the stratosphere. Ocean impacts create cavity collapse patterns that depend strongly on water depth. In deep ocean basins, the initial impact creates a transient cavity in both the water and underlying seafloor. The cavity walls collapse inward, generating a complex pattern of waves that propagate outward at speeds approaching 200 meters per second in deep water. These waves maintain their energy over vast distances, only slowing and growing in height as they encounter shallow water near continental margins. Near-shore impacts combine the worst aspects of both scenarios. The initial blast excavates both seafloor and water, creating massive local tsunamis that strike nearby coastlines within minutes. Simultaneously, the impact generates atmospheric effects comparable to continental strikes, including dust injection and thermal radiation that can ignite fires hundreds of kilometers away. The 500-meter scenario would likely generate tsunamis with initial wave heights of 10 to 50 meters, depending on impact location and seafloor geology. These waves would lose energy as they propagate across ocean basins, but could still reach distant coastlines with heights of several meters. Coastal areas within 1,000 kilometers of the impact would face severe flooding, while more distant shores might experience waves comparable to major storm surges. The 3-kilometer case would create truly catastrophic tsunamis with initial wave heights potentially exceeding 100 meters. Ocean-wide propagation would carry destructive waves to every coastline within the impact basin, with arrival times ranging from hours to half a day, depending on distance and bathymetry. Even coastlines 10,000 kilometers away might face waves 10 to 20 meters high, sufficient to cause major destruction in low-lying areas. Atmospheric effects begin immediately after impact as the fireball rises and expands. The initial thermal pulse would be visible from space, briefly outshining the sun when viewed from the impact hemisphere. This intense radiation would ignite fires across vast areas, with the range depending on atmospheric clarity and the presence of combustible materials. The blast wave follows minutes later, propagating outward at supersonic speeds and gradually weakening as it spreads across larger areas. At distances of 100 to 200 kilometers from a 500-meter impact, the overpressure would still be sufficient to damage buildings and injure people caught in the open. The 3-kilometer scenario would generate destructive blast waves that remain dangerous at distances exceeding 1,000 kilometers. Perhaps most significantly for long-term consequences, both scenarios would inject enormous quantities of pulverized rock into the stratosphere. The 500-meter case might loft 10 to 100 billion tons of fine debris, while the 3-kilometer impact could inject over 1 trillion tons. This material would begin affecting global climate within days, creating the initial stages of an impact winter that could persist for years. The immediate human response would depend critically on impact location and existing infrastructure. Coastal impacts would trigger massive evacuation efforts as tsunami warnings spread to threatened shorelines. Continental impacts would overwhelm regional emergency services and require national or international assistance for effective response. Communication networks would likely suffer severe disruption within hundreds of kilometers of the impact, complicating coordination of emergency response efforts. Transportation infrastructure, including airports, seaports, and major highways, would face damage or destruction across wide areas. Power grids would fail due to both direct damage and massive demand fluctuations as populations attempted to cope with the unfolding crisis. These immediate effects represent only the beginning of a much longer cascade of consequences that would reshape human civilization and Earth's climate system. We trace these longer-term effects in the scenarios that follow, exploring how societies might adapt to a world transformed by collision with a visitor from interstellar space. Part 8, 3I-ATLAS Impact, Part 2, Atmosphere, Climate, Biosphere and Human Systems. The injection of vast quantities of pulverized rock into Earth's stratosphere begins a cascade of atmospheric changes that would reshape global climate for years to decades. Fine silicate particles measuring between 0.8 and 8 micrometers in diameter prove particularly effective at blocking sunlight while remaining suspended at altitudes above most weather systems. These particles settle slowly under the influence of gravity, but stratospheric winds disperse them globally within weeks of the impact. Recent analysis of the Chicxulub boundary layer suggests that fine dust can remain suspended for 15 to 20 years after a major impact, with the highest concentrations persisting for 5 to 8 years. During the initial 2-year period, dust loading may be sufficient to shut down photosynthesis almost completely on a global scale. Even our more modest scenarios would inject enough material to cause significant atmospheric effects. The 500-meter case might suspend 10 to 100 billion tons of fine debris in the stratosphere, enough to reduce global sunlight by 10 to 50% for several years. Agricultural regions would experience shortened growing seasons and reduced crop yields, even without complete photosynthesis shutdown. The 3-kilometer scenario could inject over 1 trillion tons of material, potentially reducing surface sunlight by 70 to 90% for the first year, and causing near-complete photosynthesis failure across the planet. Climate modeling suggests that surface temperatures would drop by several degrees Celsius within months of impact, with the most severe cooling occurring during the first year when dust concentrations peak. The cooling would be most pronounced over continental interiors, while ocean temperatures would decline more slowly due to water's high thermal capacity. This temperature differential would alter atmospheric circulation patterns, potentially disrupting monsoon systems that billions of people depend on for agricultural productivity. Target geology plays a crucial role in determining the composition and longevity of stratospheric aerosols. Impacts on sulfate-rich sedimentary rocks would release enormous quantities of sulfur dioxide, which combines with water vapor to form sulfuric acid aerosols. These particles remain suspended even longer than silicate dust and create additional cooling through their interaction with incoming solar radiation. Ocean impacts add water vapor to the stratospheric loading, but the net climate effects remain uncertain. Water vapor acts as a greenhouse gas, potentially offsetting some of the cooling caused by dust and sulfate particles. However, water vapor also participates in complex atmospheric chemistry that could enhance or inhibit the formation of other aerosols. Current models suggest that the dust and sulfate effects would dominate, but with significant regional variations depending on atmospheric circulation patterns. The biosphere response to prolonged darkness and cooling follows predictable patterns based on studies of past mass extinctions and nuclear winter scenarios. Photosynthesis-dependent organisms face the most immediate threats, while species that can survive on stored energy or alternative food sources have better prospects for short-term survival. Marine ecosystems would experience cascading effects as photosynthesis failure kills phytoplankton that form the base of oceanic food webs. The collapse would propagate upward through fish, marine mammals, and seabirds, though some deep-sea communities that depend on chemical energy sources rather than photosynthesis might remain largely unaffected. Coastal ecosystems would face additional stress from impact-generated tsunamis that would scour nearshore habitats and deposit debris far inland. Terrestrial ecosystems would show strong selectivity based on feeding strategies and metabolic requirements. Large herbivores that depend on fresh vegetation would face immediate food shortages, while smaller omnivores and detritivores might thrive on the abundant dead plant material. Hibernating species and those with low metabolic rates would have survival advantages during the initial crisis period. Forest ecosystems would likely collapse within the first year as trees die from lack of sunlight and accumulated stress. The die-off would release enormous quantities of carbon dioxide as decomposing vegetation overwhelms the reduced capacity for photosynthetic carbon uptake. This release could partially offset the cooling effects of stratospheric dust, creating complex feedback loops that are difficult to predict precisely. Human agricultural systems would face unprecedented challenges as crop yields collapsed worldwide. The 500-meter scenario might reduce global food production by 20 to 50% for several years, creating severe shortages but potentially manageable through rationing and international cooperation. The 3-kilometre case could eliminate outdoor agriculture entirely for the first year, forcing humanity to rely on stored food supplies and protected growing environments. Controlled environment agriculture, including greenhouses and indoor growing facilities, would become critically important for maintaining food production during the impact winter. These systems could operate independently of natural sunlight using artificial illumination, though at greatly increased energy costs. Societies with significant CEA infrastructure would have major advantages in maintaining food security. Cold hardy crops and preserved food stores would become strategically vital resources. Root vegetables, grains, and other crops that can tolerate shortened growing seasons might continue producing reduced yields even under partially darkened skies. Traditional food preservation techniques, including drying, fermentation, and cold storage, would extend the utility of stored supplies. Industrial systems would face severe disruptions as energy demands soar for heating and artificial lighting, while supply chains collapse due to transportation difficulties and resource shortages. Electrical grids would struggle to meet increased demand while facing reduced capacity from solar installations and weather-related damage to wind and hydroelectric systems. Fossil fuel combustion would increase dramatically, potentially accelerating the return to normal atmospheric composition, but at the cost of increased carbon dioxide emissions. Public health consequences would extend far beyond the immediate impact effects. Respiratory problems would increase as fine dust particles remain suspended in the lower atmosphere for months after the impact. Cold-related mortality would rise as heating systems struggle to maintain comfortable temperatures. Nutritional deficiencies would emerge as food variety decreases and caloric intake drops. Water sanitation systems would face unprecedented challenges as industrial capacity declines and energy costs soar. Contaminated water supplies could spread infectious diseases through populations already stressed by cold and malnutrition. Medical supply chains would be severely disrupted, making it difficult to treat both routine ailments and impact-related injuries. Recovery timelines depend strongly on the severity of initial atmospheric loading and the resilience of surviving infrastructure. The 500-meter scenario might require 2 to 5 years for regional recovery, with agricultural productivity returning to near normal levels as stratospheric dust concentrations decline. Building codes and infrastructure planning would be revised to account for impact-generated blast waves and thermal effects. The 3-kilometer case would trigger what researchers might term a dim decade of reduced sunlight and global climate disruption. Recovery would require fundamental changes in energy systems, agricultural techniques, and international cooperation mechanisms. Seed banks and genetic repositories would become crucial for restoring ecosystem diversity as conditions gradually return to normal. Underground facilities for data storage, energy generation, and food production might prove essential for maintaining technological civilization during the worst phases of impact winter. These installations would require careful planning to ensure adequate life support and connectivity during extended periods of surface uninhabitability. The human response would likely include unprecedented levels of international cooperation as nations recognize that recovery requires coordinated global efforts. Resource sharing, technology transfer, and population migration might become necessary for ensuring survival in the most severely affected regions. The crisis could accelerate development of sustainable energy systems and closed-loop agricultural techniques that would benefit humanity long after the atmospheric effects subside. Perhaps most importantly, the experience would demonstrate the vulnerability of complex technological societies to low-probability, high-consequence natural events. The lessons learned from managing impact winter conditions could inform preparations for other global challenges, including climate change mitigation and adaptation to other environmental disruptions. Recovery from cosmic collision would reshape human civilization in ways that extend far beyond the immediate crisis period. Part 9. Could we stop it? The validation of kinetic impact as a deflection technique began on the 26th of September 2022, when NASA's DART spacecraft struck the asteroid moon Dimorphos at 6.14 kilometers per second. The collision shortened Dimorphos's orbital period around its parent asteroid Didymos by 33 minutes, demonstrating that hitting a small asteroid with a well-targeted spacecraft can indeed change its trajectory in predictable ways. The DART mission measured what planetary defense specialists call the momentum enhancement factor, designated by the Greek letter beta. This parameter quantifies how much more momentum change results from an impact compared to what would be expected from the spacecraft's momentum alone. The additional momentum comes from debris ejected by the collision, which acts like exhaust from a rocket engine, pushing the asteroid in the opposite direction. DART achieved a beta value of approximately 3.6, meaning that the momentum change was nearly 4 times larger than would have resulted from a perfectly inelastic collision. This enhancement came from the plume of dust and rock fragments blasted away from Dimorphos's surface, which remained visible to ground-based telescopes for weeks after the impact. The debris plume effectively amplified the push delivered by the small spacecraft. But DART struck a very small target under carefully controlled conditions. Dimorphos measures only about 160 meters across and was struck by a 610 kg spacecraft moving at just over 6 kilometers per second. Scaling this technique up to deflect much larger objects, like our hypothetical 3I-ATLAS scenarios, requires careful consideration of how momentum transfer efficiency varies with target properties and impact conditions. The European Space Agency's Hera mission, scheduled to arrive at Didymos in late 2026, will provide crucial data for refining deflection models. Hera will map the crater created by DART's impact and measure how the collision changed Dimorphos's physical properties. This information will help scientists understand how momentum transfer depends on target composition, internal structure, and surface properties. The relationship between target characteristics and momentum enhancement remains one of the biggest uncertainties in deflection planning. Solid, rocky asteroids might respond differently than loosely bound comet nuclei. Objects with significant internal porosity could absorb impact energy without producing efficient debris plumes. Rubble pile asteroids, held together primarily by gravitational forces, might fragment rather than deflect when struck by high-velocity impactors. Timing represents the most critical factor in successful deflection. The mathematics are elegantly simple. A small velocity change applied early in an object's trajectory produces a large position change by the time it reaches Earth's orbit. A deflection of just 1 millimeter per second applied 1 year before impact would shift the object's position by roughly 32 kilometers at Earth's distance from the Sun. To ensure that a potentially hazardous object misses Earth by a comfortable margin, deflection missions typically aim for position changes of at least 10,000 kilometers. Achieving this goal requires velocity changes that scale inversely with the available time. 1 millimeter per second applied 10 years early produces the same deflection as 1 centimeter per second applied 1 year early, but the earlier intervention requires far less energy and carries much lower mission risks. Multiple kinetic impactors can provide larger deflection than single missions, but with diminishing returns due to changing target properties after each collision. The first impact might create optimal conditions for momentum transfer by fracturing the surface and creating loose debris. Subsequent impacts might be less efficient if they strike previously disturbed material or altered surface geometry. Gravity tractor techniques offer an alternative approach that works particularly well for long-term deflection campaigns. This method involves parking a massive spacecraft near the target asteroid and allowing mutual gravitational attraction to slowly modify the object's trajectory. The technique provides extremely precise control over the deflection process and eliminates risks associated with fragmenting the target. The gravity tractor approach requires years or decades to produce significant deflection, making it suitable only for threats detected far in advance. The spacecraft must also be quite massive to generate meaningful gravitational forces, potentially requiring advanced propulsion systems or multiple coordinated vehicles. But for appropriate targets and timelines, gravity tractors could provide safer and more predictable deflection than kinetic impacts. Nuclear standoff detonations represent the most powerful deflection option for large objects or short warning times. This technique involves detonating nuclear explosives at a carefully calculated distance from the target, vaporizing a thin layer of surface material and creating a powerful push through rocket-like recoil. Computer simulations suggest that properly designed nuclear deflection could change the trajectory of kilometer-scale objects by several meters per second. However, nuclear deflection carries significant technical, legal, and political challenges. The Outer Space Treaty prohibits placing nuclear weapons in orbit, though planetary defense scenarios might qualify for exceptions under the treaty's provisions for peaceful uses of nuclear technology. The Partial Test Ban Treaty prohibits nuclear explosions in space, creating additional legal complexities that would need to be resolved through international negotiation. Technical challenges include precision targeting, timing of detonation, and prevention of target fragmentation. Nuclear explosives must be positioned at exactly the right distance to maximize momentum transfer, while minimizing the risk of breaking the object into multiple pieces that could still threaten Earth. The required precision exceeds that demonstrated by any current nuclear delivery system. Ion beam deflection represents a more speculative but potentially attractive option for very long-term deflection campaigns. This technique involves using focused ion beams to gradually erode material from one side of the target, creating a steady thrust through ablation recoil. The method requires years or decades to produce meaningful deflection, but offers excellent control and minimal risk of fragmentation. Advanced propulsion technologies, including solar sails and electric thrusters, could enable new deflection approaches that are not currently feasible. Mass driver systems might collect material from the target object itself and accelerate it away at high velocity, creating thrust without requiring fuel delivered from Earth. These concepts remain largely theoretical, but could become important for dealing with the largest potential impactors. The International Coordination Framework for Deflection Missions involves the International Asteroid Warning Network for Threat Assessment and the Space Mission Planning Advisory Group for Mission Coordination. These organizations conduct regular exercises to practice decision-making processes and identify potential points of friction or delay in international cooperation. Recent tabletop exercises have highlighted the challenges of making deflection decisions under uncertainty and time pressure. Questions arise about who has authority to approve deflection missions, how to handle cases where deflection might shift the impact point from one country to another, and how to manage the risks associated with deflection failure or unintended fragmentation. The decision timeline for deflection missions depends critically on detection lead time and confidence in impact predictions. Objects discovered decades before potential impact offer multiple opportunities for deflection attempts and course corrections. Objects detected only months or years before impact require immediate decision-making, with limited opportunities for error recovery. For our 3I-ATLAS scenarios, detection would likely occur only months before impact due to the high approach velocity and relatively small size compared to the distances involved. This short warning time would severely limit deflection options and require immediate international cooperation to mount any kind of response. The 500-meter case might be deflectable with multiple kinetic impactors if detected a year or more in advance. The 3-kilometer scenario would likely require nuclear deflection for any realistic detection timeline. The success of DART has provided proof that kinetic deflection works in practice, not just in computer simulations. But scaling from proof of concept to operational planetary defense requires continued investment in detection systems, deflection technologies, and international cooperation frameworks. The mathematics of orbital mechanics provide clear guidance about what works and when, but implementation remains a challenge that requires sustained effort and forward thinking. We develop these capabilities not because impact is imminent, but because the alternative is unacceptable. The universe operates on timescales that dwarf human civilizations, but occasionally those vast timescales intersect with our brief moment on this planet. When they do, our response will depend on choices we make today about technology development and international cooperation. Part 10. What if Oumuamua hit instead? The first confirmed interstellar visitor, Oumuamua, presented a very different profile from the scenarios we've explored with 3I-ATLAS. Discovered in October 2017, as it was already leaving the inner solar system, this strange elongated object measured roughly 100 by 30 by 30 meters, comparable in size to a city block, but moving at 44 kilometers per second relative to the Sunday. For our analysis, we consider Oumuamua as a representative 100-meter diameter sphere to simplify energy calculations. At interstellar velocity, such an object would deliver approximately 190 megatons of kinetic energy upon impact with Earth. That's roughly 20 times more powerful than the 1,908 Tunguska event, which flattened 2,000 square kilometers of Siberian forest, and nearly 400 times more energetic than the 2013 Chelyabinsk fireball that injured over 500 people with its shockwave. The key question for a 100-meter impactor is whether it would survive atmospheric passage to create a surface crater or break apart in an airburst explosion. The answer depends on the object's internal strength, composition, and entry angle. Oumuamua's unusual elongated shape and tumbling rotation suggested a solid, coherent object rather than a loose collection of fragments which would favor survival to ground impact. Entry dynamics for such an object begin at an altitude of roughly 100 kilometers, where atmospheric drag first becomes significant. The leading surface heats rapidly to thousands of degrees as it compresses and displaces air at hypersonic velocities. For rocky objects with reasonable structural integrity, the critical question is whether dynamic pressure exceeds the object's tensile strength before it reaches the ground. Dynamic pressure peaks at altitudes between 20 and 40 kilometers, depending on entry angle and atmospheric conditions. At Oumuamua's velocity, this pressure would approach several 100,000 pascals, equivalent to roughly 3 atmospheres of pressure differential between the leading and trailing surfaces. Most rocky materials can withstand such pressures, but objects with significant internal fractures or weak compositional boundaries might break apart under this stress. If Oumuamua survived to ground impact, it would excavate a crater roughly 1 to 2 kilometers in diameter, depending on target geology and impact angle. The immediate devastation would extend perhaps 10 to 20 kilometers from the impact point, with severe structural damage and fires caused by thermal radiation from the fireball. The blast wave would remain dangerous to human life at distances up to 50 kilometers, breaking windows and damaging buildings across a much wider area. The Chelyabinsk comparison provides useful context for understanding these effects. That 18-meter object exploded at an altitude of 30 kilometers with an energy release of roughly 500 kilotons, creating a shock wave that damaged thousands of buildings and injured over 500 people with flying glass. The injuries occurred despite the airburst happening at high altitude, demonstrating how even elevated explosions can cause widespread damage through atmospheric shock wave propagation. Scale Oumuamua's energy up by a factor of 400, and the potential for destruction increases dramatically. An airburst at 20 to 30 kilometers altitude would create overpressures sufficient to level most buildings within 20 to 30 kilometers of the explosion point. The thermal flash would ignite fires across hundreds of square kilometers, while the shock wave would cause structural damage and injury at distances exceeding 100 kilometers. But unlike our larger 3I-ATLAS scenarios, a Oumuamua scale impact would produce minimal global climate effects. The object simply lacks the mass needed to inject significant quantities of dust into the stratosphere. Local and regional smoke from impact-triggered fires might create temporary cooling effects downwind of the impact site, but these would dissipate within weeks or months as atmospheric mixing disperses the aerosols. The regional impact footprint would depend strongly on impact location and local population density. A strike in a major metropolitan area could cause casualties in the millions, primarily from structural collapse and fires, rather than direct impact effects. The economic consequences would propagate globally through disrupted supply chains and financial markets, but the physical effects would remain confined to the immediate impact region. Rural impacts would cause much less immediate human suffering, but could still trigger significant secondary effects. Major transportation infrastructure, including airports, seaports, and highway intersections, could be disabled by impacts hundreds of kilometers away if the shock wave timing coincided with critical operations. Power grid failures might cascade across wide regions as transmission lines and generating stations suffered damage. Agricultural impacts would vary seasonally and geographically. A strike during harvest season could destroy crops across thousands of square kilometers through fires and shockwave damage. Livestock casualties could number in the millions if the impact occurred in major ranching regions. But these losses would represent local rather than global food security challenges. The atmospheric entry process itself would create spectacular visual effects visible across hundreds of kilometers. Oumuamua's high velocity would produce an extremely bright fireball, potentially outshining the sun for observers within a few hundred kilometers of the trajectory. The object would be visible in broad daylight for several minutes before impact, appearing as a brilliant streak across the sky, accompanied by sonic booms audible at great distances. Seismic effects would extend the impact signature far beyond the immediate blast zone. A 190 megaton ground impact would generate earthquake-like shaking with magnitudes reaching 6 to 7 on the Richter scale within 100 kilometers of the impact point. This seismic energy would trigger landslides in mountainous terrain and could cause structural damage to buildings already weakened by the atmospheric shock wave. The psychological impact might prove as significant as the physical damage. Unlike earthquakes or severe weather, which occur with some regularity and predictability, a major asteroid impact would represent an unprecedented disaster type for modern human civilization. The sudden appearance of a brilliant daytime fireball, followed by massive destruction, would challenge existing disaster response frameworks and emergency planning assumptions. Recovery timelines would be measured in years rather than decades. Unlike the global climate disruption possible with larger impacts, a Oumuamua scale event would allow normal agricultural and industrial activity to continue outside the immediate impact region. International assistance could flow freely to affected areas without the constraints imposed by worldwide food shortages or climate disruption. The event would likely catalyze major improvements in planetary defense systems and international cooperation frameworks. A demonstrated impact from interstellar space would provide unambiguous evidence that such events pose real rather than theoretical threats. Funding for detection systems and deflection technologies would almost certainly increase dramatically in the years following such an impact. Insurance and reinsurance markets would face unprecedented challenges in assessing and pricing risks from future cosmic impacts. Current actuarial models have no historical basis for evaluating asteroid impact probabilities and consequences. A Oumuamua scale impact would provide the first modern data point for such assessments, likely leading to significant changes in how societies prepare for and respond to low probability, high consequence natural disasters. Building codes and infrastructure planning would be revised to account for shockwave and thermal effects from potential future impacts. Critical facilities including hospitals, emergency services, and communication networks might be hardened against blast effects or relocated to reduce their vulnerability to cosmic impacts. The scientific value of such an event would be enormous, providing direct measurements of impact processes that are currently studied only through computer simulations and geological evidence from ancient craters. High-speed cameras and seismic monitoring networks would capture detailed data about crater formation, shockwave propagation, and debris distribution patterns. But the human cost would be measured in lives disrupted and communities destroyed rather than civilizational collapse. A Oumuamua scale impact would represent a regional catastrophe comparable to major earthquakes or volcanic eruptions, severe and tragic for those directly affected but manageable within existing international disaster response capabilities. The contrast with larger impact scenarios highlights the importance of early detection and deflection capabilities. Objects in the 100-meter size range remain difficult to detect until they're relatively close to Earth, providing limited time for deflection attempts. But they're also small enough that kinetic deflection missions remain technically feasible with current or near-future capabilities. The real Oumuamua passed safely through the inner solar system and returned to interstellar space, carrying with it answers to questions about the composition and structure of materials formed around other stars. But its brief visit demonstrated that interstellar objects do reach the inner solar system, and that future visitors might not follow such benign trajectories. We prepare for the possibility that the next Oumuamua might be aimed more directly at our world. Part 11. Law, Ethics, and Geopolitics of Last-Ditch Choices. The legal framework governing planetary defense operates within a complex web of international treaties that were written without considering the specific challenges posed by asteroid and comet threats. The Outer Space Treaty of 1967 establishes that space is the province of all mankind and prohibits placing nuclear weapons in orbit or on celestial bodies. But the treaty's provisions for peaceful uses of nuclear technology might allow exceptions for planetary defense scenarios. The Partial Test Ban Treaty of 1963 prohibits nuclear explosions in the atmosphere, underwater, and in outer space, creating another potential obstacle to nuclear deflection missions. More recent agreements, including the Treaty on the Prohibition of Nuclear Weapons that entered into force in 2021, add additional layers of complexity by prohibiting the use or threatened use of nuclear weapons for signatory nations. These treaty obligations create significant legal ambiguities in scenarios where nuclear deflection might be the only viable option for preventing a catastrophic impact. International law provides mechanisms for emergency exceptions to treaty obligations, but invoking such exceptions requires broad international consensus and clear evidence that the threatened harm exceeds the risks associated with treaty violation. The question of who has authority to authorize planetary defense missions becomes particularly complex when deflection actions might shift an impact point from one region to another. A marginally successful deflection could transform an ocean impact into a continental strike, or move the point of impact from a sparsely populated area to a major metropolitan region. These possibilities create profound ethical dilemmas about acceptable risks and equitable burden sharing. Current international coordination mechanisms operate through the International Asteroid Warning Network for threat assessment and the Space Mission Planning Advisory Group for mission planning. But these organizations function primarily as advisory bodies without formal authority to approve or coordinate deflection missions. National governments retain ultimate decision-making authority over space missions launched from their territory or by their agencies. The time pressure associated with impact threats could severely strain existing diplomatic processes. Traditional international negotiations operate on timescales measured in months or years, while deflection missions might require launch decisions within weeks or days of threat confirmation. Emergency procedures would need to be established in advance to enable rapid decision-making without abandoning principles of international cooperation and consultation. Liability issues add another layer of complexity to deflection planning. If a deflection mission fails partially and changes the impact location rather than preventing it entirely, which parties bear responsibility for the consequences? Current space law assigns liability to launching states for damage caused by their space objects, but the application of this principle to planetary defense scenarios remains untested and potentially problematic. The distribution of deflection capabilities among nations creates additional geopolitical tensions. Currently, only a few countries possess the space launch capabilities needed for deflection missions, while many more would be affected by impact consequences. This asymmetry raises questions about how deflection decisions should be made and whether nations with deflection capabilities have obligations to act on behalf of the global community. Nuclear deflection scenarios present the most challenging legal and political problems. The nations with the largest nuclear arsenals are not necessarily the same ones with the most advanced space capabilities. Coordinating nuclear deflection missions might require unprecedented cooperation between nuclear weapon states and spacefaring nations, potentially involving transfers of nuclear materials or weapons technology that are normally prohibited under non-proliferation treaties. The dual-use nature of deflection technologies creates additional concerns about weaponization and arms control verification. Kinetic impactor spacecraft designed for asteroid deflection could theoretically be used against satellites or other space assets. Nuclear devices designed for deflection missions could potentially be adapted for weapons use. International monitoring and verification systems would need to be developed to ensure that planetary defense preparations do not become covers for weapons development. Public communication about deflection decisions involves balancing the need for transparency with the risk of creating unnecessary panic. Government officials would need to explain complex risk assessments and technical trade-offs while maintaining public confidence in the decision-making process. The experience of the COVID-19 pandemic has demonstrated both the importance and the difficulty of maintaining clear public communication during global emergencies. Different cultural and religious perspectives on risk acceptance and technological intervention could complicate international consensus building. Some communities might view attempted deflection as inappropriate interference with natural or divine processes, while others might consider failure to attempt deflection as unacceptable negligence. These philosophical differences could affect both domestic political support and international cooperation. The economic implications of deflection missions would likely dwarf the costs of any previous space endeavor. A comprehensive deflection campaign involving multiple spacecraft and international coordination could cost hundreds of billions of dollars and require industrial mobilization comparable to major wartime efforts. Decisions about cost sharing and resource allocation would need to be made under extreme time pressure, with imperfect information about mission requirements and success probabilities. Insurance and financial markets would face unprecedented challenges in managing risks associated with both potential impacts and deflection mission failures. Current catastrophe insurance models have no framework for evaluating global-scale risks or the effectiveness of technological interventions. The interconnected nature of modern economies could amplify financial disruptions far beyond the immediate physical effects of either impacts or deflection attempts. Regional security concerns could complicate deflection efforts if impact threats coincide with existing international tensions. Military capabilities needed for deflection missions might be viewed with suspicion by potential adversaries, while the coordination required for effective deflection could be difficult to achieve among nations with strained diplomatic relationships. The precedent established by the first major deflection mission would have lasting implications for future planetary defense efforts. Successful international cooperation could strengthen frameworks for addressing other global challenges, while failures or disputes could undermine future cooperation when it might be even more critically needed. Environmental considerations add another dimension to deflection decision-making. Nuclear deflection missions would involve detonating nuclear devices in space, potentially creating radioactive debris that could affect spacecraft operations and space exploration for years or decades. The environmental costs of deflection must be weighed against the consequences of allowing impacts to occur. The question of democratic participation in deflection decisions presents fundamental challenges for representative government. The technical complexity of impact risk assessment and deflection planning makes it difficult for non-experts to evaluate proposed courses of action. But the global consequences of these decisions suggest that they should not be left entirely to technical experts and government officials. International law provides some guidance through principles of state responsibility and international cooperation, but the specific application of these principles to planetary defense scenarios would likely require new treaties or agreements developed specifically for impact threats. The window for developing such agreements may be limited, as the urgency associated with actual impact threats could preclude careful deliberation about legal frameworks. The ethical framework for evaluating deflection decisions involves balancing risks, benefits, and uncertainties across multiple dimensions, including technical feasibility, international law, environmental consequences, and equitable burden sharing. These decisions would likely need to be made with imperfect information under severe time constraints, creating conditions where moral clarity becomes particularly challenging to achieve. We explore these dilemmas not because they represent abstract philosophical puzzles, but because future deflection missions will require international cooperation on an unprecedented scale under conditions of extreme urgency and uncertainty. The legal and ethical frameworks we establish today will shape how humanity responds when the next visitor from space follows a trajectory that threatens rather than merely intrigues. Part 12. A future where the sky is watched. The transformation of planetary defense from science fiction concept to operational capability began with the patient work of sky surveys that scan the heavens each clear night, cataloguing the movements of objects both familiar and strange. Tonight, as automated telescopes capture images of distant asteroids and occasional visitors from interstellar space, we stand at the threshold of unprecedented awareness of our cosmic environment. The Rubin Observatory in Chile now sweeps the southern sky with its 8 4-meter mirror and 3, 2-gigapixel camera, producing a detailed census of moving objects throughout the solar system. Each night brings terabytes of data processed by algorithms that can distinguish between main belt asteroids, near-Earth objects, and the rare visitors from beyond the realm of planets. The facility's deep, rapid surveys should detect interstellar objects weeks or months earlier than previous generation instruments, providing crucial additional time for tracking and characterization. NEO Surveyor, scheduled for launch in late 2027 or early 2028, will add space-based infrared observations to complement ground-based optical surveys. Operating from the gravitationally stable L1 Lagrange point, this specialized telescope will detect asteroids and comets approaching from the direction of the Sun, filling a major gap in current detection capabilities. The combination of ground-based optical surveys and space-based infrared observations should dramatically improve our ability to find potentially threatening objects years before they pose immediate risks. The success of the DART mission in 2022 has validated kinetic deflection as a practical technique for changing asteroid trajectories. When the DART spacecraft struck Dimorphos at over 6 kilometers per second, it shortened the small asteroid's orbital period by 33 minutes and created a debris plume that remained visible for weeks. The measured momentum enhancement factor of 3.6 exceeded expectations, demonstrating that carefully targeted impacts can efficiently transfer momentum to asteroid targets. The European Space Agency's Hera mission will arrive at the Didymos system in late 2026 to conduct detailed forensic analysis of the DART impact site. Hera will map the crater created by the collision and measure how the impact changed Dimorphos's physical properties, rotation state, and internal structure. This information will calibrate computer models used to design future deflection missions, turning deflection from experimental technique to engineering discipline. But technology alone cannot ensure planetary defense success. The international coordination frameworks established through the International Asteroid Warning Network and Space Mission Planning Advisory Group provide mechanisms for sharing observations, coordinating follow-up campaigns, and planning collaborative responses to confirmed threats. Regular exercises and simulations help identify potential points of failure and develop procedures for rapid decision-making under pressure. The mathematical reality of deflection remains elegantly simple. Small velocity changes applied early produce large position changes by the time an object reaches Earth's orbit. A deflection of just 1 millimeter per second applied 10 years before potential impact creates a position change of roughly 320 kilometers at Earth's distance from the Sunday. This relationship strongly favors early detection over last-minute intervention, making continued investment in survey capabilities the most cost-effective approach to planetary defense. Future deflection missions will likely employ multiple techniques depending on the specific characteristics of threatening objects and available warning time. Kinetic impactors work well for solid targets discovered years or decades in advance. Gravity tractors provide precise control for long-term deflection campaigns. Nuclear standoff detonations offer high-energy options for large objects or short warning times, though with significant legal and political complications that would need to be resolved through international negotiation. The development of rapid response characterization missions using small satellites and rideshare opportunities will enable detailed study of newly discovered threats within months rather than years. Understanding an object's composition, structure, and rotation state becomes crucial for designing effective deflection missions and predicting their outcomes. Advanced propulsion systems, including ion drives and solar sails, could enable these characterization missions to reach targets more quickly and operate for extended periods. The expanding catalogue of near-Earth asteroids provides growing confidence that we have identified most objects capable of causing global catastrophes. NASA's surveys have found more than 90% of kilometer-scale near-Earth asteroids, meaning that surprise impacts large enough to trigger mass extinctions have become extremely unlikely. But completeness drops rapidly for smaller sizes, and the discovery rate for city-killer-scale objects in the 50 to 500 meter range continues to accelerate. Long-period comets and interstellar objects present ongoing challenges due to their unpredictable arrival times and high approach velocities. Current statistical models suggest these events remain rare on human timescales, but their high kinetic energies make them potentially dangerous, even at relatively modest sizes. Improved survey capabilities should provide earlier warning for most such objects, though some approaches from the direction of the Sun may remain difficult to detect until after closest approach. The lessons learned from managing the COVID-19 pandemic have highlighted both the importance of international cooperation during global emergencies and the challenges of maintaining coordinated responses across different political, systems and cultural contexts. Planetary defense scenarios would likely require even higher levels of cooperation due to the technical complexity of deflection missions and the global nature of impact consequences. Public education about asteroid and comet risks remains crucial for building support for planetary defense investments and ensuring rational responses to future impact threats. The dramatic but low probability nature of cosmic impacts makes them difficult to communicate effectively without creating either inappropriate alarm or dangerous complacency. Clear risk scales like the Torino system help translate complex orbital mechanics into understandable threat assessments. The economic benefits of planetary defense extend beyond catastrophe avoidance to include scientific discovery, technology development, and international cooperation frameworks that have value independent of their defensive applications. Asteroid characterization missions provide insights into the formation of the solar system and the distribution of potentially valuable resources. Deflection technologies advance propulsion systems and precision navigation techniques with applications throughout space exploration. Climate change and other environmental challenges have demonstrated humanity's capacity for both remarkable technological innovation and frustrating political gridlock when addressing long-term, global-scale problems. Planetary defense presents similar challenges, but with more favorable political dynamics due to the clearly external nature of the threat and the unambiguous benefits of successful intervention. The story of 3I-ATLAS illustrates both the current capabilities and remaining limitations of planetary defense systems. We detected this interstellar visitor promptly, characterized its basic properties, and confirmed its safe trajectory within months of discovery. But if the same object had been approaching on a collision course, we would have had only limited time to mount any kind of deflection response. Future interstellar visitors will likely be detected earlier as survey capabilities improve, providing more time for characterization and potential deflection if needed. The combination of ground-based and space-based surveys, improved linking algorithms, and rapid response follow-up campaigns should extend warning times and improve our understanding of these exotic visitors from other star systems. The development of planetary defense capabilities represents one of the few areas where human technological advancement directly addresses existential risks that have shaped Earth's history for billions of years. Major impacts have repeatedly altered the trajectory of biological evolution, most famously ending the age of dinosaurs 66 million years ago. For the first time in Earth's history, an intelligent species has developed the ability to detect and potentially prevent such catastrophic collisions. This capability carries responsibilities that extend far beyond our own species. Earth hosts the only known example of complex life in the universe, harboring millions of species and ecosystems that have no voice in decisions about planetary defense. The choices we make about survey investments, deflection technologies, and international cooperation frameworks will influence the trajectory of life on Earth for generations to come. The sky that once seemed fixed and predictable has revealed itself to be dynamic and occasionally dangerous. Objects wander between stars on journeys that began billions of years ago and may continue for billions more. Occasionally, these wanderers find inhabited worlds in their path, creating moments of intersection between cosmic-scale processes and the brief spans of individual civilizations. We cannot predict when the next such intersection will occur, but we can prepare for the possibility that it will happen within the span of human civilization. The tools we develop, the international frameworks we establish, and the knowledge we accumulate will determine whether future encounters with visitors from space continue to inspire wonder or become agents of destruction. Two trajectories cross the inner solar system in our imagination. One carrying 3I-ATLAS safely past Earth at a comfortable distance, the other bringing a similar object into collision with our world. The difference between these paths may be measured in kilometers of space, but the consequences span the difference between scientific curiosity and civilizational crisis. Which trajectory we encounter depends on the random dynamics of objects scattered throughout the galaxy billions of years ago. But our response to that encounter depends on choices we make today about watching the sky and preparing for what we might find there. The universe is vast, ancient, and largely indifferent to human concerns. But it is not entirely unpredictable, and it is not entirely beyond human influence. In the careful mathematics of orbital mechanics, in the patient accumulation of observations by automated surveys, in the international cooperation frameworks that span political and cultural boundaries, we find the foundation for a future where cosmic collisions become predictable challenges rather than random catastrophes. The sky is watched, the tools are ready. The question that remains is whether we will continue to develop these capabilities with the sustained effort that planetary defense requires. The answer to that question will be written not in the stars, but in the choices we make about technology, international cooperation, and our commitment to protecting the world that gave rise to intelligence capable of contemplating its own cosmic context. We are the first generation with the ability to defend our planet from cosmic collision. Whether we will also be the generation that ensures this capability survives and develops may determine the long-term trajectory of life on Earth.